Good evening, sir. Good evening, students.
Good evening, sir.
Very good evening. So, which topic we discussed yesterday?
Surface chemistry.
Okay. I think we have to start organic today, right?
Yes, sir.
Okay, then let us start haloalkanes and haloarenes. First chapter in second PU. So, two questions will come from this chapter. Okay. So, let us see first preparation methods. Preparation methods. The first one, from alcohols. So in this, we have different methods. First one, let us see Groove's process. What is Groove's process? When alcohols treated with concentrated HCl in presence of anhydrous zinc chloride, then you will get RCl plus H2O. Okay, now here mixture of concentrated HCl plus zinc chloride. This is known as, what it is called? Lucas reagent. Okay. Now, order of reactivity of alkyl halides, alcohols with Lucas reagent. Primary alcohols, secondary alcohols, tertiary alcohols. Okay, so primary alcohols. So here we add one more point before that. Before going to order of reactivity, add one more point. Anhydrous zinc chloride acts as anhydrous zinc chloride acts as Lewis acid. Lewis acid. It helps in cleaving CO bond. What is its role, sir? It cleaves in alcohol CO bond. Okay, then order of reactivity. Primary alcohols will give with Lucas reagent. no turbidity. Secondary alcohols gives turbidity within 5 minutes. Tertiary alcohols give immediately. So tertiary alcohols are more reactive. So order is 3 degree greater than 2 degree greater than primary, right? So this order of reactivity of alcohols with low cost reagent. Next, with PCl3 and PCl5. With PCl3, 3 moles of alcohol reacts with PCl3, gives rise to 3 moles of alkyl chloride plus H3PO3, phosphorus acid. Whereas PCl5 gives you 1 mole of alkyl chloride plus POCl3 plus HCl. Next method is Dodgins method. Dodgins method. What is Dodgins method? That is with thionyl chloride, SOCl2. So ROH plus thionyl chloride, SOCl2 gives rise to RCl plus SO2 plus HCl. So here the byproducts formed are gases. So you'll get pure alkyl chloride. You'll get pure alkyl chloride. Done. Next. So this is first method from alcohols, right? Second method, halogen exchange methods. Halogen exchange methods. What are they? That again, subdivision is there. First one, Finkelstein reaction. What you'll get? C2H5Br, sodium iodide in acetone. And what you'll get? C2H5I plus NaBr. So what you'll get? Iodoalkanes. In Finkelstein reaction, you'll get only iodoalkanes. You'll get only iodoalkanes. Next. Schwarz reaction. AgF. C2H5F plus. So here you will get only fluoroalkanes are obtained. In Schwarz reaction, you will get only fluoroalkanes. Then NBS. What is NBS? N-bromo succinamide is used for bromination at allylic and benzylic carbon. which is N-bromosuccinimide, sir. So when it is treated with, let us suppose, toluene, CH3, then bromination will take place at benzylic carbon. Yeah. Right? So this is benzylic carbon. Okay. Next reaction, borodine Hunsadeker reaction. When silver salts of carboxylic acid treated with bromine in presence of carbon tetrachloride, then you will get so this is alkyl bromide. Instead of using bromine, if you are using iodine, then you won't get alkyl iodide, but you will get ester. You get ester. Now this reaction is known as Birnbaum-Simonini reaction. Birnbaum-Simonini reaction. Done, sir. So this is about preparation methods of haloalkanes. Next, chemical. Okay, I'll give you one generalization regarding physical properties. Physical properties. So I'll give you some generalizations so that you can use it for remaining all other compounds also. So boiling point is directly proportional to molecular mass. A boiling point is directly proportional to length of carbon chain. Boiling point is inversely proportional to number of branches, or one more property, that is solubility, is inversely proportional to molecular mass. Next property, order of density. Ri greater than, Rbr greater than, RCl greater than, Rf, alkyl fluoride. Order of bond strength. What is bond strength? CH3F. Methyl fluoride is greater than methyl chloride, methyl bromide, methyl iodide. Next one. Order of dipole moment. CH3Cl greater than CH3F, CH3Br, CH3I. So these are some important points regarding physical properties. Then let's move to chemical properties. What are chemical properties? So here, nucleophilic substitution reactions. The first one, let us see, SN2 methyl, methyl bromide. It is treated with a base like OH minus. And what you will get, CH3OH plus Br minus. Now let us see mechanism. H H Yeah. Who is approaching? Nucleophile. Now, this cannot attack from front side. So it will attack from the back side. And what happens? There is a bond formation between nucleophile and carbon, and bond breaking between carbon and bromine. Okay. Now this is what we call transition state. Then finally the bond between carbon and bromine will break, and bond is found between carbon and nucleophile. This is our product. Now here, OH minus is placed exactly opposite to that of Br minus. So this is what we call inversion of configuration, or this is also known as Walden configuration. Right. So this is about stereochemical aspects of SN2 mechanism. And then here, so this is a slow step. It's rate determining step. RDS means rate determining step. This is fast step. Okay, now in the rate determining step, both substrate as well as nucleophile is present. So rate of reaction is proportional to concentration of reactant as well as nucleophile. So what is order set? 2. Molecularity 2. So it follows second order kinetics. It follows second order kinetics. One note you write here. Polar aprotic solvents are favorable for SN2. What are polar aprotic solvents? DMF, dimethyl formamide. Dimethyl formamide. What does that mean? So this is dimethyl formamide. One more example is there. DMSO, dimethyl sulfoxide. Dimethyl sulfoxide. Done, sir. That is what we call DMSO, dimethyl sulfoxide. Last point. Vinyl and aryl halides do not undergo SN2 mechanism. Done. So this is all about SN2. Next, SN1. So let us see SN1. Example, CH3 taken thrice C, Br, SOH minus gives rise to tertiary butyl alcohol. Now, so this is mechanisms. In that, let us see first step 1. In step 1, what happens? Cleavage of CBr bond. Now here carbon gets positive charge. 2 departed Br minus. So this is a slow step. It is known as rate determining step, RDS. Next step 2. Now, when the carbocation is formed, what is hybridization of carbon? EsP2 shape, trigonal planar. Now, this sp2 hybridized carbocation, who is approaching nucleophile. Now, nucleophile can attack from front side as well as back side. It attacks from back side. H this is inversion of configuration. This is retention of configuration. So this mixture is called racemic mixture. You're getting racemic mixture, right? So this is about SN1 and SN2 mechanism. Next, elimination reactions. In that E1 mechanism, okay. So let us see E1. So try to understand the mechanism. Tertiary metal iodide, iodide will depart here, minus I minus. So this is always slow step. What you are getting C plus CH3, CH3, CH3. Next, step 2. Now base will come into the scene. Now this base will abstract this proton, and this bond will come here. What you are getting CH3C, CH3 double bond CH2. What you are getting, sir? So what you are getting? Alkene. So final product is alkene. So E1 mechanism C1 mechanism is favored by weak bases like H2O, alcohols. Okay. Next mechanism, E2 mechanism. So this is also known as beta elimination 1,2 elimination or trans elimination. This takes place in presence of strong bases. What are they? Alcoholic KOH, ethoxide, sodamide, tertiary butoxide. Okay. So let us see example for this. What you're getting are CH double bond, CH2, so alkene you are getting. Okay. And it is favored by strong bases. Example. What is example? Two bromobutane. Sorry. It's also CH3. Okay. Now halogen attached carbon. This is halogen, sir. This is halogen. Attached carbon. This is alpha carbon. This is what we call alpha carbon. This is alpha carbon, right? This is alpha carbon. Adjacent carbons are called beta carbons. Now two beta carbons are there. So that means we can eliminate hydrogens from these two beta hydrogens. But which one is more favorable? Which one is more favorable? Right? So according to Sage-Jeff's rule, this hydrogen is eliminated. What you are getting? CH3, CH double bond, CH, CH3, 2 butene plus If this hydrogen is eliminated, then what you will get? CH2 double bond CH, CH2 Br, 1 butane. But according to Saint-Jeff's rule, this is a major product and this is minor product. Because according to Saint-Jeff's rule, beta hydrogen is eliminated from carbon having less number of hydrogens. This is what we call Saint-Jeff's rule. Done. Other chemical reactions that action of KOH. If it is aqueous KOH, then nucleophilic substitution cell. If it is alcoholic KOH, what is alcoholic KOH? Its role is dehydrohallucinating agent. What is alcoholic H? Both hydrogen and halogens are eliminated. And it will get C2H4. That is CH2 double bond CH. Alkene you will get. Next, with moist Az2O. What is moist Az2O? H2O plus Az2O. Then you will get 2 AzOH. Then C2H5Cl plus 2 moles of AgOH. What you will get C2H5 nucleophilic substitution. C2H5OH here plus AgCl precipitate you will get. Next with alcoholic KCl. Being ionic in nature, KCN. You use Cn minus. Yeah. So a silver cyanide is basic in nature. So its covalent bond is present between carbon and carbon, carbon and silver. And what you will get C2H5, NC plus NC. So here you are getting isocyanide. With KCN you will get cyanide, with AgCN you will get isocyanide. Done, sir. So this is all about important chemical reactions, right? Some other important reactions. Williamson's synthesis. When alkyl chloride treated sodium ethoxide minus NaCl. What you will get C2H5O, C2H5. Very important Woods reaction. You know very well, right? When alkyl halide treated with sodium metal in presence of dry ether, then minus 2NaX, you get RR. That means alkanes you will get. Last one, with ammonia. If you take C2H5Cl plus ammonia, eliminate HCl. And what is remaining? C2H5 and H2 plus minus HCl. One more C2H5Cl minus HCl again. C2H5 taken twice in H. Then again we use one more C2H5Cl excess minus HCl. Done, sir. So this is about quaternary ammonium salt. Done. Just make a note of all these reactions and study these reactions for 5 minutes. We'll start questions. So shall we proceed for questions now?
Yes, sir.
Okay. Okay, let us start. First question. The compound A on treatment with sodium gives B, and with PCl5 gives C. B and C react together to give diethyl ether. A, B and C are. A, B and C are. Okay. Let us write that sequence. A on treatment with sodium giving B. Now B, PCl5 gives C. Now B and C gives diethyl ether. That means C2H5O, C2H5. Now this is the given sequence. Now when you will get diethyl ether, if B and C are alkyl halide and sodium alkoxide. Sodium alkoxide, right? Then what should be those products? So let us suppose compound A is C2H5OH. On treatment with sodium, you will get a B, isn't it? What is that B we will get here? H plus will be substituted by Na plus. Right? So this is B, isn't it? Now, okay, here we should, it's not the sequence, A only. So A only with PCl5 gives C. Okay, again A, C2H5OH plus PCl5 gives C2H5Cl. Okay, plus POCl3 plus HCl. This is C. Now B and C reacting together to give C2H5O, C2H5O plus NaCl. So Williamson synthesis. Na plus Cl minus eliminate, remaining C2H5O, C2H5. So that is you are getting diethyl ether. Diethyl ether. Right? So this is about question number 1. Next question. Second question. Which of the following acid does not exhibit optical isomers? Which of the following acids does not exhibit optical isomerism? Options. Okay. Which of the following acids does not exhibit optical isomers? So optical isomerism means you should have at least one chiral center. That means 4 different substituents. You should have 4 different substituents. Let us see malic acid. Malic acid is this. Okay. Now, this carbon is having 4 different substituents. No. This carbon is having no 4 different substituents. No. So, this is optically inactive. So it does not exhibit optical isomerism. Next, related to this, one more question. Which of the following is an optically active compound? Options: 1 butanol, 1 propanol, 2 chlorobutane, D 4 hydroxy heptane. 4 hydroxy heptane. So let us suppose 2 chlorobutane you consider, sir. Now you consider this carbon, right? Now this is one substituent, this is another, this is another, this is another. So all 4 substituents are different. So this is what we call chiral. So hence it is optically active. What is chiral carbon? Carbon having 4 different substituents. So that carbon, second carbon is having 4 different substituents. So the compound is optically active. Next question. Benzene reacts with N-propyl chloride. N-propyl chloride in the presence of anhydrous AlCl3 to give three propyl 1-chlorobenzene N-propyl benzene no reaction isopropyl benzene. Right, let us consider N-propyl chloride. CH3, CH2, CH2, Cl. Now AlCl3. Take this along with chlorine. So what you are getting? CH3, CH, H, CH2 plus. So this is primary carbocation. So in order to get more stable carbocation, this will take place 1,2 hydride shift. What is that 1,2 hydride shift? So here, this hydride shift to this carbon. You know what you're getting? CH3, CH. Now that hydrogen is taking that bond pair of electrons. So this carbon gets positive charge. What type of carbocation? Secondary. We know that secondary carbocation is more stable than primary carbocation. Now this is more stable. Now this will react with benzene. CH is having CH3. So what is this? Isopropyl benzene. So fourth option is correct. Done. Next question. Reaction of tertiary butyl bromide with sodium methoxide produces what it will produce. Sodium methoxide, it produces this base, right? Okay. Then we are getting CH3, C plus carbocation is generated. Now this CH3 for alkanes, I'm writing like this. This is one CH3. Now sodium methoxide produces CH3O. What you're getting? CH3C double bond, CH2, CH3. Alkene you are getting there.
Excuse me, sir.
Yes.
What about NA, sir?
Okay. So Na plus D parts. And finally, what you're getting? CH3O minus. Now this acts as a nucleophile. Na plus is eliminated. That is why, because oxygen is more electronegative than sodium. So oxygen will take up that electron pair, and sodium is departing as Na plus. Na plus ion. Clear?
Yes, sir.
The next question. Which of the following pairs of compounds are enantiomers? Which of the, do you know enantiomers? Following pairs of compounds Okay. So which of the following are enantiomers? Do you know what are enantiomers?
Optical active isomers which are non-superimposable mirror images of each other are called enantiomers.
We are reading statement or what?
Sir, ಅವಾಗ ಓದಿದ್ವಿ sir exam ಅಲ್ಲಿ. On that time we studied for exam, sir.
Just give me simple answer, not statement.
Isomers which are not superimposable of each other images.
What are non-superimposable?
Don't know, sir.
Enantiomers means, yeah, your statement is correct. Isomers which are mirror images to each other and non-superimposable. Now, let us consider first compound. Let us assume there is a mirror here. This is a mirror. Now, this is the compound, and can you say this is its mirror images? Mirror image?
Yes, sir. Yes, sir.
So these two are mirror images, right?
Yes, sir.
Then keep this mirror, this image over this second image. This is, let us suppose first, this is 2. Keep the first compound over the second compound. Okay. Let us suppose you bring this molecule and place over this molecule. Then, if you bring this molecule and place over this molecule, here which group is present?
Alcohol.
OH group, right? So this group will fall on here, right? Here, what is that group?
Hydrogen group.
Okay, both are matching.
No, sir.
Now here, this image, this hydrogen will fall over this OH, right? Both are matching.
No, sir.
So that is completely mismatch. If you place this image over this image, then no two groups will match, sir. So complete mismatch. So that is what we call non-superimposable. Is what we call non-superimposable. Do you understand? So first compound is satisfying both the conditions like mirror images and non-superimposable, isn't it?
Yes, sir.
So first option itself is your answer. So that is what we call enantiomers, right? One more definition is there. Diastereomers. What are diastereomers? Isomers which are not mirror images. They should not be mirror images, sir. But they should be non-superimposable. So this is the only condition which differ from enantiomers. In enantiomers, isomers should be mirror images to each other. But in diastereomers, isomers should not be mirror images. Did you understand?
Yes, sir.
Yes, sir.
Now in those 4 options, can you find out how many diastereomers are there? Already first one we found that it is enantiomer. Then B, C and D, can you find out whether they are enantiomers or diastereomers? Definitely not enantiomers. Then how many are diastereomers there?
Yes, sir. 3, sir.
Remaining 3 are diastereomers. Image.
Yes, sir.
Here this is a H, this is a OH. So not mirror image, right?
Yes, sir.
That we can consider as diastereomer. Here it is H, but here what is coming? OH. So this is also not mirror image. So it will be diastereomer. Here H, here OH. Not mirror image. So this is also considered as diastereomer, right?
Yes, sir.
Yeah. So that's it for this session. Tomorrow we'll start alcohols, phenols, and ethers. Okay, study all those reactions. Definitely, you can answer all questions from haloalkanes and haloarenes. 2 questions will come. Okay. So that's it for this session. Meet you tomorrow once again. Then we'll discuss alcohols, phenols, and ethers. Right? Anyhow, I'll send this notes in our group. Just if you want, you can check.
Yes, sir.
Okay. Good night, all of you. Then meet you tomorrow.
Thank you, sir. Bye, sir.
Bye bye. Good night.